we're going to think about, I have an object A cruising along to the right. I have an object B cruising along to the left. They will run into each other. They'll run into each other, and I'll just put a little dotted line at the point where they will run into each other. So this first scenario, they're heading towards each other, playing a game of chicken. Then they will meet at this point, and they will separate at this point, and box A, B, D. And even though I can't draw it like it, all those box A's there that are drawn should be the same size. All the B's should be the same size. And then they will go their separate ways. A's goes this way, and B's going this way. So, while the two boxes are touching each other, so during the collision, the contact of the collision, there are three quantities that are the same for both objects. And I will say that one of those quantities is so incredibly obvious that people generally don't think about it. And this is basically the introduction into the next two chapters, actually. And the materials on the last test. So, start out with, what are the quantities?
Forces?
Pardon?
Forces?
You need to be more specific.
Speed. Friction.
They exert the same friction on each other?
No, normal force?
You're saying that they exert the same normal force on each other?
At a point? Are they moving at the same speed and are they at the same distance apart from each other? Like from the middle part?
I mean, A is closer to the dotted line than B is, so B must be traveling faster.
Oh.
Yeah.
Okay, so I'm just making sure I have the thing right. So do they meet up in the middle?
They meet at the dotted line.
There's two
not
dotted lines.
the first line.
This dotted line. That's where they meet. This is the dotted line right here is when they separate. So this is when they first touch, this is when they last touch, and then they go their separate
Oh,
ways.
they keep touching for a little bit.
Yeah.
Oh, okay.
So they meet at the dotted line, which is explicitly not the middle point between the both of them.
Correct.
Okay.
Does that mean like A pushes B a little bit?
Yeah.
And is that where it's controversial?
Oh,
No,
yeah.
no, the controversial is I knew she was gonna leave, and so I commented to her that
Yeah, he was just saying something.
Oh.
if I say something, you should wait till I say something controversial and then storm out.
Just being silly with it.
So anyway, back to the forces. So how do I know that they're not exerting the same normal force on each other?
Because A pushes B a little.
Not for that reason.
He's going faster. Or
Yep.
something like that.
They saw contact.
Say it again?
They're not in contact at the end.
Nope, that's not the issue. And after, when it's non-contact, there's no normal force exerted on each other.
A weighs more?
Nope. We don't know relative masses of the two.
A pushes B.
So then,
Okay. And
And I guess that shows that it has more normal force since it has to push it past the, what they know.
A pushes B more than B pushes A.
no,
Was it just the wording that you want?
A has more acceleration?
nope. I don't know which one has more acceleration.
A is exerting more force on the B than B is exerting on the A.
That is definitely not true.
Okay, then. The opposite way around?
If they,
That is definitely not true.
okay, what
if
was
they
it?
exerted the same force, they would just go like this instead of like that.
Nope.
Okay, okay.
Could be the time,
Sorry?
the time it takes for the A to contact B and then.
Question.
Wait, I would,
Is that?
you trailed off there, Giovanni. Did you want to flesh that out some?
Okay, so like the time,
This is what-
A contacts B, since like A is closer to the line.
I don't even know
Um,
that percent.
I guess the more time it has in contact, that I guess that's the reason it pushed it.
So you're saying A is touching B longer than B touches A?
No, never mind, I don't think that will.
Question.
Alan?
What was the question?
The question is, while they are in contact, from this point in time to this point in time, while they're touching each other or in the collision, what are the three quantities that are the same for both?
Position.
When you talk about the position of an object, typically, unless you want to get into more detail, the position is the center of mass. So, assuming even distribution, the positions are not the same.
Okay.
So what will be the time that they are in contact with each other?
One more time,
The time they're in contact with each other?
is what?
Same.
And that's the one that's so obvious that most people don't think about it. They will touch each other for the same amount of time. Generally, when a class gets sort of caught up on that one, I give them a clue. It's the name of a Bobby Sherman song.
That probably.
And that generally gets that kind of look of who is Bobby Sherman. And I will say, I did have a student one semester who had actually been to a Bobby Sherman concert.
Did they get it?
No, they did not get that one, but he knew who Bobby Sherman was, which is the closest anyone has gotten.
Yeah, there you go.
Singer of the 70s. I would say at this point, a mediocre singer from the 70s, but.
Yeah, he did top Disco Duck.
He was hitting his stride before Disco Duck. My issue with Disco Duck is not the quality of the singing, more of the in content. Bobby Sherman would be the other way around. All right, so they touch each other for the same amount of time. There's one. Let's get back to the forces. We're close on that one, but suddenly we went astray.
Friction?
Let's not talk specific forces at the moment.
Okay.
Although it would be a normal, well, probably a normal force guaranteed. Any other forces we don't know.
So there is no force then.
There is indeed. They're touching each other.
Do we know if gravity is affecting both of them?
We don't know.
Okay.
Well, the gravitational force from a planet, we don't know. This could be a universe with just these two objects that meet, or there is a gravitational pull between them. So we could include that if we want to. However, all right. So I make the claim that
Wait, sorry. If it's not the position, what is this question?
so if A, there it is, goes from here to here, so its displacement is that. B's displacement is that. If A and B were actually drawn properly, the displacements would be the same.
That's what I meant.
And then, one more,
What three things?
and there seems to be a general forgetting of what exactly is force.
Things that generally push and pull.
What's the difference between a 2 Newton push and a 2 Newton pull?
Direction.
Ah, direction. Force is a vector. Direction matters. So how do I know that the normal force that A exerts on B is not the same as the force that B exerts on A?
Because they're going in opposite directions.
A pushes on B that way, B pushes on A that way. So the forces cannot be equal. However, what is equal?
Distance. Like
It will, displacement,
Okay.
we'll cover that.
right, sure.
What is
Well,
it?
just like generally the forces are on one another. Or no, A is pushing B, so no, they're more than B is pushing A.
Oh, be careful about that. What is Newton's third law of motion?
So the opposite reaction.
Yeah, it's that one.
Okay. Okay. I mean, are they pushing the exact amount? Or
You mean the same?
the same amount?
It is the same amount.
Okay.
It is not the same force because the directions are opposite,
Okay.
but it is the same magnitude of force. That's Newton's third law. When two things collide, unless Newton was full of it and all of the physics that we have up till now is complete bunk, they will exert the same magnitude of force on each other. I'm gonna go ahead and write that in shorthand notation. Over here, I'll put absolute values around it for magnitude of force. Or in shorthand notation, the force on A from B is equal to the negative of the force on B from A. This is just shorthand for Newton's third law. So, this is the force on A from B. And the force, there's a line of sight right there. Force on B from B.
Okay. This is the three things they share in common with each other when they are colliding.
Yes.
Okay.
All right, what's the point of this? And I will say for most routes, they generally get the force thing first and time last, so way to be different. If I look at these two concepts, I will end up with this idea of momentum and impulse. This is chapter 8. If I look at these two, I get this, I get the idea of work and energy. And this is chapter 7. And so we will start out with work and energy, then after that, we'll bring in momentum and impulse, and then after that, we'll combine the two. But it's a different way of looking at the same stuff that we have been looking at, but in more difficult situations. Another thing to keep in mind, momentum and impulse are vectors. Work and energy are scalars. And so we will abandon, well, semi-abandon vectors for a little bit. Which does give us the advantage of looking at a situation, looking at a problem in terms of work and energy. The big plus is we're not dealing with vectors. Unfortunately, the big minus is we're not dealing with vectors, and we lose some information about direction. Momentum, the big plus is that we don't lose that information about direction. The big minus is the fact that we're keeping track of direction. So first off, work. Which is why I don't use a capital W for weight. Work is force times displacement. And I use, well, I just wrote the word out. Sometimes I use X instead of S, it's just another one of the letters that commonly used. I feel like we have done dot products, at least talked about dot products. Let's do more in this context here. So I have a box on the ground, and I'm pushing on it this way, and the box moves this way. So this is delta S. This is the force. And it has some velocity at this point that's going to change. Is the force helping the movement or hurting the movement or having no direct impact on the movement?
Helping.
Okay, so if I do a dot product between force and displacement, I should get a positive answer. So this force is doing positive work on the box. So the box is moving to the right, some displacement, delta S, and this time the force is acting against it. Is this force helping or hurting the movement?
Right.
So the work is negative. The force is doing negative work on the box. And then the third scenario, the box is moving to the right with some displacement delta S, and the force is downwards. Is that force helping the movement, hurting the movement directly?
It's not affecting unless there's friction.
So if it does affect it, it's not affecting it directly, but indirectly because it affects the friction. It affects the normal force, which affects the friction. So this is doing no work. So if the force is perpendicular to the displacement, no work is done. Now, I know what you're thinking. That's what you usually are thinking when I say that. Where's the more hardcore math? So what I can care about, since I care about how much of the force is in the direction of movement or against the direction of movement, well, in this case right here, if I have a force that's going down to the right, those are supposed to be the same, and I have a displacement this way, so there's my force, there's my displacement. If I put them tail to tail, I look at the angle in between them, and I want to figure out how much of that force is in the direction of movement. So if I break that up into its components, the horizontal component is the part I care about. The vertical is not helping or hurting directly. And this red bit right here, the horizontal component is just going to be F times the cosine of theta. So this is the same as the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. So that's really convenient if you're given force and displacement in polar form. So if I have a force that is, say, let's stay away from the unlucky numbers right now, 15 newtons at an angle of negative 30 degrees. So it's a force that's sort of moving like that. So I have 15 newtons acting on an object that's moving in that direction. And the displacement is 4 meters and 0 degrees. What is the work being done? Well, I just multiply these two. It's a dot product. So I'm going to do 15 newtons, the magnitude of the force, times the magnitude of the displacement, times the cosine of the angle between them, which is 30 degrees. Which is crudely somewhere around 42. Well, actually, before I do that, I think Giovanni's going to correct me here in a second.
52.
One more time?
52.
52?
Yeah, 51.9 to be specific.
Oh, square root of 3, not square root of 2. Okay. Units?
Newtons.
If you're stopping there, you missed something.
Even meters.
Yes. I got 2 units here. I got a Newton and I got a meter. So Newton meters, the dot in between them to emphasize the fact that these are 2 units multiplied together. And although capital N, lowercase m you could get away with that if you did the lowercase m first, you definitely need the dot, otherwise it's millinewtons. All right, so we have 52 Newton meters. Now, there are times when you have units and you look at it and physicists go, God, that is so much to write. Surely we can come up with something simpler. And so they did. In this context, we're talking about work and energy. A Newton meter is a joule. Symbolized by capital J, this is a joule. A joule, by definition, is a Newton meter. Or a kilogram meter squared per second squared. Or for grams of it, kilogram meter squared seconds to the negative 2. Now later on when we get to chapter 10, 9 and 10, Newton meter will not be equal to a joule. So it depends upon context. Questions up to here?
That's a S to the negative 2.
Yes. All right, let's do another quick example here. I have a force of 5 newtons I hat. So establish I hat, J hat. Minus 3 newtons J hat. I have a displacement of 6 meters I hat plus 7 meters J hat. So if I sketch that out, see 6 meters I hat, 7 meters J hat, so let's go somewhat in that direction right there. There's my displacement. And the force acting on that object while it does it is 5 newtons, 3 newtons. So it's more I than J. Not quite perpendicular. Now, if I've drawn it even remotely accurate, then I should expect a positive answer. But what is the work being done? Well, you multiply the parallel parts.